Very good. Well, thank you very much, Elizabeth. And also thank you to the other organizers, to Raymond and to Eckhart and to Michael. Thanks for putting together this very nice program. It's been very exciting and illuminating for me to see some things that are quite different, and also for the chance to share this work. So what I'm going to talk about today is all about fairly concentrated suspensions, but going over two different regimes. One is going to be very, very concentrated, where we're considering shear thickening behavior and trying to understand contact networks, and then also some inertial flow transitions. So the concept of transition between either properties or flow states is sort of the unifying theme of this talk. And so in case I get close to the end and don't have time, I want to make sure that I thank the people who did the work. So I'll be talking about work of a former student, Mercedes, current postdoc, Aritra Santra, who will be going to Indian School of Mines in Dhanbad in January, former PhD student Madhu Maji, and then a colleague, Lina Barudi from Manhattan College. And I want to give special credit to Roman Marie and Ryohei Seto, who have developed a set of codes that we use, and those are also available by GitHub. I'll mention that again later. This is work I've done with Mort Den and Sanjoy Banerjee at City College, and then Bulbul Chakraborty at Brandeis. And of course, we fund it any way we can, but oddly enough, this is funded partly by the National Science Foundation, partly by a food company, and partly by an oil extraction company. Okay, so suspensions are multiphase flow, so we're in a multiphase flow meeting here. And they're particles, solid particles suspended in liquid. So I'm going to be talking about solid particles in liquid, ranging in principle over very wide range in scales, from down in the 10 nanometer scale for these colloidal dispersions, up through cellular dispersions and onto wet sand. And that unifying feature is that the hydrodynamics of the fluid matters, and also the excluded volume of the particles always matters. There can be many other forces that play a role. But suspensions in nature had a strange intersection with this conference, with KITP in 2018, at a meeting that I was a co-organizer for, dense suspensions. There was also this period of mudslides right before the beginning of the meeting. And so this is a picture from just down the highway on 101 in Montecito, about 100 miles farther north in San Luis Obispo. You see also on the 101 that there's a similar mudslide. And you see that this is basically just a river of mud, so particles in fluid. And this was quite a disaster. And of course, if any of you were trying to get to this meeting before the highway was opened, it was quite an adventure. And there was some sampling of this material. Doug Gerelmach's group sampled some of this mud, and he just shared this paper on the results of the rheology of this material, and some of this rheology is quite similar to what I'll be talking about today. And there was also a poster by Shravan on Monday. So I think it's clear that fluid mechanics of suspensions has some major consequences in geophysical scenarios. And my perspective is that property and flow models are clearly needed to be able to make progress toward prediction of phenomena and rational understanding. The complexity of these can be enormous, the different forces, the size scales, and so forth. So I'm going to be talking about a model material, which I'll call the near hard sphere suspension. And the relevance of using this suspension for developing fluid mechanical understanding is something I made a little perspective paper on a couple of years ago. Okay, so the two transitions that I'm going to talk about for the rest of the talk, I want to first outline. First, I'm going to talk about this abrupt shear thickening. It's a rheological property transition driven by changing the shear rate or the stress. And here you see this is results that go back 50 years, but it was known even 30 or 40 years before that. But this was the first work which really did it with nice monodispersed spheres, right? And so what Hoffman showed was that as you increase the volume fraction of these spheres in the liquid, you went from a non-Newtonian response with respect to the viscosity as a function of the shear rate. Here it increases at a certain level and shear thickens, but as you increase the concentration, it eventually becomes discontinuous. And you get orders of magnitude change in the properties eventually. So this is typically over 50% in volume fraction. And I'm going to describe this in terms of simulations which address this property. But then if you drop the concentration, the stuff can flow. And that's what those mud flows are indicating, is that there can be this significant transition. And we're going to study this in the suspension, in the Taylor-Couette flow for suspensions, up to about 30% in our experiments and up to 40% in some others. It's been studied. And so the picture is this, that you go, as you increase the rotation rate of an inner cylinder, this is a view of the flow from the outside of a two-cylinder Taylor-Couette experiment. You go from just a nice circular Couette flow to the Taylor vortices, very beautiful structures, and then you get a spiraling structure. So we'll come back to that later in the talk. Okay, so let me back up just a bit. I want to first talk about this case now and describe our simulations just in briefest terms. If you're interested, the method is laid out in quite a bit of detail here, and then references back to that work. You can find more details on newer versions. So we call this lubrication flow DEM, and so there's friction, hydrodynamics, and a repulsive force included. The contact model is very much from the Kundel and Strack approach in the early DEM. And then a key point is that this conservative force, or a stabilizing repulsion, gives the rate dependence to the material. That is, it determines what level of forcing is necessary to drive the particles into contact. So we solve then a zero Reynolds number on all scales equation. We balance forces and torques. So here's our equation of motion, and you're saying, well, that's a force balance. Why isn't that static? It's not static because the hydrodynamic forces require motion in order to exist. And so if you need hydrodynamic forces to balance your equation out, then you have the motion that's seen. Okay, so the forces that we include, I just want to give a pictorial version of those. That is that we consider the hydrodynamic interactions, of which the dominant one, but not the only one we include, is the squeeze flow lubrication. So this says if I'm trying to bring two particles together, I have to pump the liquid out of the gap between them, and that results in a large force, which in fact is scaling as 1 over the gap size. And we regularize that singularity at h equal to 0 to allow contact to happen. So when contact happens, then we have a friction, which has a friction coefficient mu, a standard Coulomb friction, saying that if the tangential stress is less than mu times the normal load, then I stick, and if I go above that, then I slip. And then we keep just one friction coefficient. We have only the single mu meaning I don't have a dynamic and a static friction coefficient. And then there's the repulsive double layer force. You could also have a model for grafted chains, but the double layer force, the basic idea is that if I had particles which had charged surface in an aqueous environment, then I will have a double layer of ions which shields that charge. And this gives a rate dependence, because if I shear the system slowly, the particles stay out far from one another. If I shear it harder, then they're driven into contact with one another. And so we've done quite a number of comparisons with experimental data. This one compares well, so I'll show it. This is comparing against Norm Wagner's, some work from Norm Wagner's group at Delaware, where they've done enormous amounts of experiments on these type of systems. And so what we see is that if we tune our model a bit here at the 56%, which actually agrees best with 51% in the experiments, because they're more monodispersed than our simulations. So there's this bit of difference in the concentration. But with that offset, then we're able to replicate much of the behavior of this system. And so what we see then is that we also predict for these colloidal particles of about 200 nanometers in radius that the repulsive force at contact, which is associated with this double layer force, would be on the order of 100 piconewtons, or 0.1 nanonewtons. And that actually turns out to be a fairly reasonable value from AFM experiments. So we've talked about this over the last decade, so I don't want to dwell on this, but the basic behavior, for those who aren't familiar, is that this lubricated to frictional scenario, where you start off at lower concentrations with lubricated interactions that then become dominated by friction at higher concentrations here, you see a continuous shear thickening that gets steeper and steeper until you have a discontinuous shear thickening. And then you can actually have this multi-valued scenario, and then shear jamming can occur. Okay, so this is actually a system where it flows at low stress, but if you go to high enough stresses, it will turn around in shear rate and go to zero. That is, shears at low stress, you try to shear it faster, it actually jams. So you go to larger stress, and it stops. And this is actually seen with the classic oobleck, which is cornstarch in water. It's been shown that this behavior is actually seen. So that's all captured in a flow state diagram, which is here a dimensionless stress and a volume fraction. And so here we have the continuous shear thickening at low enough volume fractions over all stresses. But once I get to some critical volume fraction, if I increase the stress, I will eventually see a discontinuous rise in the viscosity of the material. So that's the DST region. If I cross over this volume fraction, phi j mu, which is the jamming fraction for the frictional material, when the material is driven at high enough stress, it starts to thicken, but it thickens to infinite viscosity, meaning it jams. Okay, so that's this part of the flow state diagram. So this is the jamming line, the stress-dependent jamming line, and this is just the geometric frictionless jamming, which Corey can tell you more about. And he's probably forgotten more about this than I'll ever know. Okay, so I want to now talk, though, about how the contact network evolves as we change the conditions. So this picture at the top shows the viscosity that is simulated for a 56% suspension. And here you go from the low viscosity state, and I'm showing here the frictional contact network as well as a snapshot of the particles, which shows you basically nothing. But if I look at the frictional contact network, you can probably tell this is being sheared like this. That's the way we always do it in North America. And so this is the compressive axis of the material. And then when we go to the high viscosity state, this contact network ramifies in all directions. It percolates in all three directions. And if you're a granular person, you're asking, if it percolates in all directions, how can it flow? Right? And so it can flow because, it can flow because some of these contacts require the flow to exist, right? And so if they require the flow to exist, then this is a continuously breaking and reforming network. So the message there is that stress induces contacts, and there is a sort of a feedback mechanism because the contacts create structures which then are able to bear more load, right? And so here I'm plotting Z, the contact number on average for a simulation box of 1,000 particles, as a function of the dimensionless applied stress. And so we see that it goes up, and for 54 to 56%, I see these mildly different curves. But these curves have quite different rheology. You have a CST and then a DST, and going to this S-shaped curve. And so these curves, the solid curves, are actually from the Weierton-Cates theory. For those who aren't familiar, this is a two-state theory which has been very successful in describing this picture that we're simulating. And so we've laid out how we address getting those curves in a separate paper. So there's quite a significant difference in the rheology of these different curves, but there is a unique relationship for any volume fraction of Z versus sigma stress. So to address the network, I want to begin with contacts and the percolation of contact, because there was some idea that when I have a percolated contact network, I would suddenly get a change in the behavior. So here I'm plotting, and so this is just keeping in mind what the rheology actually looks like. But here, the largest connected cluster, or component as it's called in the network theory, stated as a fraction of the total particles in the simulation box. And we see mild differences over these three different conditions, and you're going up to nearly all the particles being in the largest cluster here at values of Z, the average value of contact number being, frictional contact number being about 3.5. What we see here is a quantity that's called the network susceptibility. And this quantity, it's shown in terms of the mathematics here, But the key point is that it diverges at percolation, right? And so what we see here is you can see the divergence is at this point at very low values of Z, about 0.3, meaning many of the particles are not participating at all in the contact network. So this is Z over all particles, not the Z of the particles in the network. So this is kind of a difference between the way granular people talk about this and suspension people talk about it, because in suspensions, you're constantly recruiting and then giving particles back to the in and out of the network as you flow. But so what we see then is that it's not a very good discriminator between CST and DST. So we really don't see much from the percolation there. So we moved on to consider what's called K-core. We've bowed to the east, we've bowed to the west in terms of the network. And so I'm going to describe what we've found from the K-core approach. So the K-core is defined based on actually social networks, was the first place it came in back in the 1980s. And so it's the K-core, the max K-core is the maximal subgraph with degree at least K. And so you obtain the core structure and the shell structure by an iterative pruning. So here's the basic idea is that if I want to find out the particles that are in the 1 core but not in the 2 core, then I can determine that by pruning away the particles with 1. And each time if I prune away a particle with 1, this one then has just 1, so I have to prune it again. So there's this constant pruning such that I get a structure where it has K contacts mutually with others in the same set. Okay, so that's the concept of the K-core. And so what we find from our simulations is that the fraction of particles which are in a given core or shell is essentially a universal function of Z for these volume fractions, except in this region where there's the onset of the 3 core. Okay? So first you have the 1 core, which grows until you start to have 2 cores forming, at which point this becomes 1 shells, and this decreases, and more of the particles are recruited into the 2 core, until this point at which, and this is a result that's rigorous from mathematics that I don't understand at all, so I can't prove that it's rigorous, but somebody did, and this actually discontinuously jumps. The 3 core arrives full-blown, spanning the entire system, out of a 2 core. And so it says that it's a very non-local event in the sense that adding 1 more contact affects a large region in a network sense. So the question is whether it does so in a mechanical sense. Okay, so again, here's the rheology for these different cases. And we're seeing that in this region at the CST-DST transition, there is some significant change. So what we did was to try to ask, well, mechanically, what's going on? And so we sampled the stress per particle by what core, the maximum core it existed in. And so here, I'm going to consider these 2 points, X and Y, X being on the CST line and Y being on the DST line at the steepest slope of the viscosity curve. And that turns out to be right where I get the onset of this 3 core. So the steepest rise is at the onset of the 3 core. At this point on the CST curve, what I see is that the probability of a given stress state, and that's the stress per particle based on K here, doesn't depend on which core it's in, right? The 3 core arrives right below all of the other cores. There's slight deviations in the others, but they all have a very similar mean stress per particle. On the other hand, so that's the data I just showed. When I go to that onset of DST, suddenly I added 0.01 in the volume fraction. Suddenly I have an order of magnitude difference in the stress per core, right? So the particles in the 3 core have a much larger stress, and that pulls the overall average up significantly. So that's one observation that we have been able to take from this. But it doesn't tell us anything a priori about the mechanics. So we went back to 2-dimensional simulation. So you can simulate in 3D or 2D. You can't do the experiments in 2D, and nobody's figured out how yet. But you can put particles in a plane and just shear, so you can get a 2-dimensional representation. And phenomenologically, the behavior is essentially the same. And so here what we're seeing is the shear rate as a function of stress. So where this becomes flat is the onset of DST, where these curves go down and back up, or they have a flow curve with a maximum, as it's called. Then we have the DST. And eventually, at this condition, which is 80% by area fraction here, we get jamming. So I'm saying mu is about infinity. We take a mu of 100. And so why do we do this? This is just helpful in terms of theoretical ideas. That is, if particles are pushed with any normal load toward one another, it's very unlikely that they will slip, right? And so it just gives us a case that's maybe the easiest to think about in that regard. And so what we find, if you look at the distribution, as you increase the stress for these, this is 74%, which is CST, and 76, which is the onset of DST. This is the first place where the triply contacting particle becomes the peak value, is at 76%. And so 3 frictional contacts in 2D gives the potential for local rigidity. And so that's the mechanical idea that we're working on. And very nice, I mean, I think a very important paper in this area has just come out on arXiv. Manuela Delgado's group with Nick Marty's at NIST, addressing some similar ideas, different language, but similar ideas. So we used what's known as the pebble game. So for those who are in the granular field, this may be quite familiar. It's using Maxwell Calodyne counting arguments to determine whether you have locally rigid structures. And so this is from Jacobs and Hendrickson. The method we're using is due to Silke Henke's work. So here we have the probability distribution of clusters of a given size normalized by the total number of particles in the simulation box. And what we see is very similar to what's seen in compressed granular materials, is that there is a power law distribution of this. And as we go to high enough volume fractions, this is at 78%, then we start to see system spanning rigid domains. But these rigid domains are still flowing. So what that means in terms of the rigidity is something that we're still exploring, because in fact, you have pictures like this, that you have little, very small domains of rigid at low stresses over where you would be typically on this end of the curve. But then you get domains that look like this. This is actually very close to the jamming state in this picture, but there are still certain of the particles which are forced to move, and so the structure is still evolving. And we have to give some thanks to Mike Vanderneld, a PhD student with Heinrich Jaeger, for helping us with the pebble game. So I want to offer a hypothesis of what's going on here that goes back to this picture. So we've sampled the maximum cluster size, rigid cluster size. This is actually showing the median of the maximum taken over many, many samples in the simulation. And what we see is that remains very small at the onset of shear thickening, and then it rises up to be essentially nearly the entire system for these higher volume fractions. So our hypothesis is that rigidity itself, the development of local rigidity beyond a single particle scale, is an order parameter for the system. And the onset of rigidity then implies DST. So here's I guess the basic picture. You have to continue this lower line, which is the onset of DST, out here to get all the states, because I can develop rigid structures out here as well. But there's no rigid structures below that line. And then above, you have rigid structures. Oh, sorry. And so the idea is that crossing that line then is the onset of rigid clusters and of the DST. Okay, so in the 5 or 7 minutes that Elizabeth may give me, I'm going to talk about finite Reynolds number cases. So everything I've talked about to this point was 0 Reynolds number. That should have been to 0, sorry. And for particles up to about 100 micron, if the fluid is viscous enough, you can get this. But it turns out in water, you can quite easily get significant Reynolds number, even at the particle scale, down into the few micron size. And people found this out in microfluidics. And so my goal here is to try to advance the fluid mechanical paradigm for suspensions, meaning trying to understand that balance between viscous and inertial effects that is at the heart of fluid mechanics, so that we can use some of the things that we've learned studying the Navier-Stokes equations to study these more messy materials. And so the one phenomenon that everybody probably has heard of is the tubular pinch or inertial migration phenomenon. And this goes back to the early 60s in Segre and Silverberg's work. And so here you see the concentration across a channel, which is originally uniform in concentration, as it goes downstream, becomes pinched to a particular location on the at about 0.6 of the radius for very small values of the Reynolds number. And this has been used to good effect in geometries that are in microfluidic devices, because you can then separate out the particles. And some very nice early simulations by Tony Ladd's group at University of Florida showed that you could get transitions of the stable states depending upon the Reynolds number. But so we wanted to use sort of the best studied flow, laboratory studied flow in fluid mechanics to try to address developing results for suspensions that would give us results that models could be compared against. So this is a classic, this is taken from a classic paper on Taylor-Couette flow by Anderich et al. And so you start out, so here you can have two Reynolds numbers. The inner and the outer cylinder can be rotating, co-rotating, counter-rotating, and so forth. And so we're going to actually consider cases only with the inner cylinder rotating. But if you look at the circular Couette flow, at low enough values of this inner cylinder rotation, you'll always be in the circular Couette flow, which I'll call CCF. Then you go to higher values, and over a wide range, you get this classic Taylor vortex flow, very beautiful. And then these become unstable to waviness, azimuthal waviness. And you can get all of these flows along this axis. If you go off that axis by counter-rotating the cylinders, you can get a spiral vortex flow. So we're going to be doing experiments along this line, only rotating the inner cylinder, but it turns out that for the suspension, we'll actually see this state. And so that's like a punchline if that the dynamical system is altered by the particle fraction. Okay, and so I want to emphasize one key point that is sort of basic to the way I look at this system, is that we worked very hard to make sure the particles were the same density as the fluid, because any sedimentation means we're not really studying a single material, and we want to study one material. Right? So we've worked very hard to keep the density of the particles in the fluid the same. So these are our experiments. There's been related experiments. I've seen that Mahbub Alam has been online quite a bit, and they've done some beautiful experiments, extended the conditions, and done some very nice things there. And that we have a review of basically the entire database of experiments on this that's coming out next year. So there's sort of a growing number of groups who are examining this question. Okay, so here's what happens for a pure fluid. So just to show the basic idea, you increase the Reynolds number, and eventually you get the Taylor vortices, then the wavy Taylor vortices, and so forth. Okay. So the inertial migration that I raised earlier is seen very beautifully here in a dilute condition. So this is the initial time and later, and the particles have migrated to these particular locations on those vortices. And that's done, there's no centrifugal force here because the particles are the same density as the fluid. So they're migrating due to their interaction with the fluid and the presence of the nearby walls. But we wanted to understand this flow also without migration, right? So I love particle migration, but in this case, we wanted to avoid it. And it turns out the migration has quite major effects on the transition, and we've studied that later, but I'm going to describe work where we tried to avoid the migration. So how do we do that? We start off in the wavy Taylor vortices, the wavy Taylor vortex state, and then we down ramp with a slow decrease of the Reynolds number as a known function of time. And so here it is going down and down. We take pictures along this line, just a single pixel or 2 pixels, and then we project those out, and that becomes a spatiotemporal diagram, which gives us the Reynolds number dependence. So you can read this as either time, or because I know the Reynolds dependence on time, that's just a Reynolds track of the behavior. So what we see here is the wavy Taylor vortices going to the Taylor vortices going to the circular Couette flow.
Just saying how you define Reynolds number? Oh, please.
Yep. Here's how I define Reynolds number, and importantly, the Reynolds number involves the viscosity of the suspending fluid. So the suspension, not just the suspending fluid. So we account for the dissipation due to the particles. So here is the case for Reynolds number for volume fraction 0, and the values for our ratio of the inner to the outer cylinder agree very well with literature values in terms of the transition from the wavy Taylor to the Taylor and to the circular Couette flow. For the suspension of just 10% particles, there's two key features. One is that this goes through a transition at a considerably lower Reynolds number, 125, from the wavy to the Taylor vortex. So this is the Taylor vortex state. But then there's this other non-axisymmetric state that's actually seen in between that isn't seen for the pure fluid. Okay, so we see this non-axisymmetric state. And then the transition back to the circular Couette is actually at a significantly lower Reynolds number. And so here's the pure fluid, and I'm going to show some movies now where this is the movie window, doing this just for the suspension, and you see these different states as we go from the wavy to a Taylor vortex to a spiral to a ribbon state and back to a circular Couette. So okay, I'm about 2 minutes from there. So here's a circular Couette flow, and these little worms have been the word of the meeting, it seems. These little worms are actually, because we have black tracer particles and we just put 20 pictures together, I think it is, and so you see the particle tracks based on those particles, and they'll have different lengths because they're at different velocities, different depths. Okay, so that was circular Couette. Here's what the Taylor vortex looks like. Okay. So you can see how the particles move, but that's a well-known flow. Here, then, we're seeing the wavy vortex flow. Here's the spiral, and so this, how are we visualizing this? We actually have flakes of a material, the very low volume fraction that reflects light, so a kaleidoscope basically, and so we see that this is a progression, but the particles don't follow that motion. That's information, if you will. That's a phase, not the particle motion. And then here's a ribbon state, which is this spiral in one direction and then the other direction interspersed with one another. Okay. So a key result as you go to higher concentrations is this, that the wavy spiral vortex at 30% solids, we do not see any axisymmetric states after we transition away from the circular Couette flow. So we have this wavy vortex flow that gives rise to a spiral vortex flow, and then it decays away into the circular Couette flow. So the flow state map here, if we're just having the pure fluid, this would be the states that we would see here, and then it becomes quite rich as we move away from the zero volume fraction case. And depending on where we are, we can go wavy Taylor to Taylor vortex and down to the spiral vortex, or we can go from wavy spiral to the spiral vortex, and you can actually go through a ribbon state. Okay, so let me summarize. The lubricated to frictional scenario that I showed for shear thickening involves basically hydrodynamic interactions, which you could call contacts, giving way to actual contacts in this model, and that gives us then a force or a stress network. And this is constantly forming and breaking, and I think shear-induced rigidity may play a key role here. Taylor Couette flow suspensions, one thing we see is a reduction in the primary bifurcation Reynolds number at all phi, and then non-axisymmetric states that are not seen in the inner cylinder for a Newtonian fluid are seen for the suspension. That's one thing. And then we see these primary bifurcations to the non-axisymmetric states. And so philosophically, for me, in terms of understanding the flow behavior here, getting to where we have established models that give us a fluid mechanics for these materials could allow a much better discussion of phenomena among people, because we would all have the same language. So thank you very much.
Thank you, Jeff, for this very great talk and many problems. Okay, who wants to question? Okay.
Hello.
Hi, Corey.
Hi, Jeff. It's Corey.
Hi, Corey.
When in the first part of your talk, when the system approaches the shear jammed regime, are the lubrication forces swamped by the contact frictional forces?
Yes, they're swamped, but they can't be zero because I need them. So, for example, if I fix the stress and the contact stresses give me 96%, I still have to get 4% from the fluid mechanics, and that determines the rate that's
Can I
necessary.
take it, can I keep going 99, 1%?
Yes, yeah.
So do you think that, so what I'm thinking about is that maybe if you have a certain friction coefficient at that shear jam line, maybe you could infer shear thickening at finite hydrodynamic forces by increasing the friction coefficient.
You
I
mean,
know it's a crazy idea, but I'm just saying, if you're at the shear jam line at a given friction coefficient,
yes.
that's dominated by all the contact forces, and then I can get sort of weaker or less compact contact networks if I go to higher friction coefficients,
Right.
even in the static limit. I'm saying, is there any analogy between that and then the finite hydrodynamic forces? Or we could just talk about it.
We'll probably have to talk about that because I'm not sure I see the picture. But in fact, things that you're talking about, I would have to say that keeping an eye on experimental work that's coming from Itai Cohen's group and Annie Colin and Guillaume Overlez's work is trying to address these sort of questions by using, for example, acoustics as a way to disrupt the networks and then find out what you get. So there may be some information. It may be a different perspective, but I do want to give a nod to that work because it's quite important, I think.
Thank you. Great talk. Thank you very much. I had a few questions of clarification. The first is sigma naught is a scaling stress. Can you remind us what that is, or at least remind me, because I missed that earlier.
I think it may have showed up, but it may not in the course of trying to make sure this fit into the time. So sigma naught is it's a very important, good question. It's the repulsive force divided by the particle size squared.
Okay.
And so it's a microscopic definition of stress at the particle scale, which then you can balance against your driving stress to determine whether you're in the hydrodynamic regime at low values of that stress, or if you push hard, then you're driven across that repulsive.
Yeah, it's fascinating how there's just different normalization stresses in these rheologies that's so indicative of I think, what the regime is in. I think that we'll hear a little bit more about that tomorrow, I'm not sure. And then I was curious, I wanted clarification about the rigid clusters versus just the clusters. How do you get that information out of your simulations? Like, what does that look like?
Well, so we know the contact state of every pair of particles that are interacting with one another. And so that determines the number of constraints on their motion, depending on whether it's hydrodynamic, none. If it's a normal contact, 1, or frictional, then 2. And you can use that in the pebble game algorithm, which is Maxwell-Caledine sort of arguments in terms of finding the particles which are rigid. And so the whole algorithm is not something I can talk about right now.
Okay, but the rigid cluster is defined in the context of that algorithm.
In the pebble game algorithm,
Okay.
That's right.
Very quick question. I feel obligated to ask about the properties of the worms. So I have to ask some question about the worms, right?
Those worms are just the tracks of tracer particles. So all you're seeing there is basically how far did that particle travel in that time. So those worms are strictly the track of a black particle and a bunch of white particles.
Thank you so much.
Yep.
Yes, I have a question about the transition in the Taylor-Coed flow. When you compare the suspension with the pure fluid, do you use the suspending fluid, or do you use the Newtonian fluid equivalent to the effective viscosity?
We always use the effective viscosity of the bulk material to describe it.
Okay.
Right? Now, there are questions about whether that's the right viscosity to use, and all I can say is that that's a measurable quantity that I can get from a rheometer experiment for that material. Whether it's right is another question. Right?
Thank you.
Yeah, but that's what we always use.
Jim?
Yeah, great talk, Jeff. So I was wondering, in most geophysical flows, we've got free surfaces. So then, of course, the stresses can't alter in the same way. So in that case, do you think a lot of the complications you have to deal with are not present, and we can just use the simpler models without jamming?
Well, okay, so it depends on just how concentrated it is and how much stress it's under, right, I guess. But because in a free surface flow, So I can have a material, and this is actually why I'm working with a food company, I guess, is that if you shear certain materials that are in simple shear would jam, the free surface allows them to deform and find a way to do something. In fact, they can fracture, whereas if they fractured, you know, if you drive them in an extrusion, they'll also be constantly fracturing but closed back up, and that's something that's done with ceramics. But in the food case, it's related to granulation. And so Mike Cates and Wilson Poon have done there's a very interesting paper from Wilson Poon's group on the granulation phenomena that you get by trying to flow above maximum packing. So the system then granulates, which I found, having worked on these for a long time, I found it very educational, let's say.
So presumably with the free surface, though, that means there's normal stress differences are important, because otherwise it would just expand vertically, and there's
yeah. Well, so I mean the experiments that have been done in Marseille on using the pressure imposed rheometer are based on that idea that if you can exchange liquid in, then you can change your volume fraction, right? And so, but if you're doing a free surface, you can't exchange in volume unless it's gas, and that's why it granulates in some sense, if the stresses are large enough to tear apart the capillary forces. So I'm not sure I answered the question really, but I think that the free surface flows are important and interesting, and this type of modeling has been used on those, but not necessarily for the extremely dense cases.
So in the first part of your talk, Jeff, you had the contact force and you had the lubrication force, and then you had a repulsive force in addition.
Mm-hmm.
Can you just briefly elaborate on the origin of that repulsive force and why that is needed?
Okay, so it's needed in order to give the material rate dependence. So that goes back to Kimberly's question, is that if I don't have the repulsive force, then whether they're in contact is purely a geometric question. It doesn't have any stress dependence. Right? But if there is this, so if there's a repulsive force, I'll come back to the origin, but if there's a repulsive force, then the particles at low stress can slide past one another, keeping a liquid layer. If they're pushed hard, then the roughness elements can come into contact, and then you're frictional. The source of this, if you do it, you can do it based on charge in an aqueous environment and getting counter ions. In many cases, like in cement, what people will do to get this behavior is throw in some comb polymers. They're polymers that have a backbone with little chains off the side, and they'll lay down on the surface, and then they'll create a brush that has a very strong sort of osmotic pressure to try to push those chains together. Mm-hmm. So those are two ways of getting that type of behavior.
Now, if you had a continuous fluid everywhere, would you still need that that repulsive force to get the rate dependence?
A continuous fluid everywhere.
So you just have a model for the lubrication force, but otherwise you don't have any hydrodynamic stress.
Oh, I see. No, because so there's been some work that was important in this area back in the 90s by John Melrose and Robin Ball, who showed that if you just consider pure fluid mechanics and rigid particles, very, very, very careful Stokes flow hydrodynamics, that you will run into an inability to flow above about 50%. The system, the gaps between particles will just collapse in finite time off to nothing, right? And so this is an important result, which I don't think is actually fully understood, but it was observed in early Stokeskian dynamics as well. You try to simulate without a little repulsive force to give the system some energy to rearrange, and it would jam at concentrations above 50%.
Okay, thanks.
Mm-hmm.
Hi, Jeff. Great talk.
I gave a plug for you.
Thanks for the props. Yeah. Noted. Okay, based on your understanding of the range where shear thickening, and in particular even discontinuous shear thickening, happens, I was wondering if you could map it to a potential geophysical flow. Like how does the parameter space where that happens map to any kind of flow in the environment? Just a curiosity question, if you can think of one.
I think I could if I was talking to the right person to give me the right data. I just don't know that I would have to get my head around that. But I think in many cases you are dealing with particles in aqueous fluid with charged surfaces, so there could be issues there. Something to think about. Right?
A quick
Okay.
one. I think I don't know what I'm talking about, but I think it may be related to Jim's question. So I think the question is, if you allow the granular to expand, I'm actually wondering, I'm thinking about Pulikam's work, then there's supposed to be a pole pressure feedback.
Oh yeah, oh
right?
absolutely.
And so how that come into what you want?
Okay, so I thought about answering Jim's question in a way that I'm going to now answer, but so in fact, okay, so there's a huge normal stress response where the viscous response goes up, and in fact, the normal stress response is usually a little bit bigger, same order of magnitude. So it's not, so you're changing your bulk friction coefficient from 0.4 to 0.3 or something like that. You know? So in fact, when you go through the shear thickening, there is a strong drive for the particles to want to dilate if they can get liquid. And coming again from Mikhail Pela's work, this is very important in turbidity current type of form, you know. So I think that's an important point, and the system will want to try to do that. In our simulations, that is probably the key issue in terms of a point that Eckhart's bringing up that we don't account for is if you have different concentrations, you would have a different non-equilibrium osmotic pressure, if you will, and you'll suck liquid from one place to another. Right? Okay.
Okay, any more questions? Thanks again, Jeff.
Thank you all.
For this great talk. So we have a break now, and we reconvene at 11.